2.2 Steady state exercise. Steady state exercise. Steady state exercise is when performing your work rate is at a constant level. This allows for your body to be able to keep the said level of exercise going for prolonged periods of time. As Adams et al. Said, your heart rate and respiratory state increase to accommodate the demands placed on your body. When exercising, this should look like someone going for a continuous same-speed jog or cycle, for example. The participant should not be short of breath or start lowering the intensity of the exercise, as they should be able to sustain it if they are working at a steady state. The effects of steady-state exercise. One effect that steady-state exercise has on the body is the heart rate. Heart rate is the amount of times your heart beats per minute. During steady-state exercise, there is an anticipatory rise in heart rate, controlled by adrenaline and noradrenaline. While during the steady-state exercise, the receptors, being baroreceptors, which detect changes in blood pressure, proprioceptors, which detect movement in the muscles, and chemoreceptors, which detect changes in blood acidity levels, start detecting movement and changes in blood pressure as exercise begins. The receptors, after detecting change, then send a signal to the cardiac control center in the medulla oblongata, telling it to speed up or slow down the heart rate. As exercise has just started, it tells it to speed up the heart rate. The cardiac control center then sends a signal down the sympathetic nervous system, which releases two hormones called epinephrine and norepinephrine. These hormones trigger the SA node to increase the firing rate of the heart, as the hormones are cardioaccelerators. The body keeps increasing the heart rate until it finds the point where the heart rate is at the point of optimum performance for the exercise intensity. So for steady-state exercise, that's around 70 to 80% of the maximum heart rate. It stays at this point until the end of exercise, where the baroreceptors and proprioceptors will detect a decrease in blood pressure and movement. They will send a signal to the cardiac control center, which will send a signal down the parasympathetic nervous system, which releases acetylcholine. This then affects the SA node by slowing down the firing rate of the heart. The slowing of the heart rate is called bradycardia. Another thing affected by steady-state exercise is stroke volume. Stroke volume is the amount of blood pumped out of the heart in a single beat. The stroke volume of a person during steady-state exercise will increase at the start of exercise. This is because the heart starts to pump out more blood per beat to allow more oxygen to get around the body quicker, as the demand for oxygen around the body grows with exercise. Around the 4-minute mark into the exercise, the stroke volume is expected to plateau until the end of exercise, as the heart has found the optimal amount of blood it can pump out per beat to match the demand around the body sufficiently. The average stroke volume for adults is roughly 70 milliliters per beat in a healthy male, whereas in elite athletes their stroke volume can vary from around 99 to 110 milliliters per beat. This is because they have worked out their cardiac muscles a lot more than average people, making it more elastic so it can stretch out further, allowing more blood into it, and is more forceful with its contractions, which means it all is pumped out of the heart and around the body. Factors that affect a person's stroke volume are venous return. This is because during exercise the muscles move, creating an increase in muscular contractions. This therefore leads to an increase in muscular pumps. This aids the blood flows venous return by the muscles contracting, which pushes on the walls of the veins, forcing the blood up through the vein through a valve which closes behind it to prevent the backflow of blood. This increases the blood's ability to return to the heart, which affects the amount the heart stretches. As the more blood fills the ventricles, the wider it has to expand. This means more blood is allowed into the heart, and therefore more is pumped out of the heart, resulting in an increase in stroke volume. Heart rate is also a factor that affects a person's stroke volume. This is because as the heart rate increases, this means the amount of blood that can get into the ventricles is decreased, as there is less time for it to fill up as the heart rate increases. This means the higher the heart rate, the lower the stroke volume to a certain extent. This is because there is a point where the heart keeps increasing but the stroke volume plateaus as it finds the optimum point for the amount of blood being let into and out of the heart. The final factor affecting someone's stroke volume is blood pressure. This is because if there is a low blood pressure, it's harder for the heart to pump blood around the body, and the venous return won't be as high, meaning less blood will be able to get pumped out. Cardiac output is the amount of blood ejected from the heart in 1 minute. Cardiac output increases as well during steady-state exercise. This is due to the heart rate increasing as well as the stroke volume. And heart rate times stroke volume equals cardiac output, so it rises and falls with the increase and decrease of stroke volume and heart rate. The average range of maximal cardiac output of an adult is 24 litres, compared to Mo Farah's maximum estimated cardiac output of 28.5 litres a minute. This shows that Mo Farah, being able to pump out an extra 4 litres of blood around his body per minute, is able to work longer and harder as his muscles receive more oxygen quicker than others, which allows his muscles to stay oxygenated and prevents them from fatiguing. Blood flow. During exercise, the flow of blood changes from going all around the body to being directed to the muscles as they need a higher amount of oxygen and energy. This happens by the precapillary sphincters leading towards more unneeded organs closing off, and ones that feed the muscles opening up more, allowing for more blood flow to them. The action of the body redirecting the blood flow to the organs, from the organs to the muscles, is called the vascular shunt. Vasodilation occurs during steady-state exercise when exercise starts, as the precapillary sphincters open up, allowing for a higher blood flow to the working muscles during the exercise, along with the precapillary sphincters vasoconstricting in some areas to lower the blood flow to less needed muscles and organs at the time of exercise to optimize performance and keep the working muscles oxygenated while they work. Blood pressure is a measure of the force that your heart uses to pump out blood around your body, and is measured in millimeters of mercury. Your systolic blood pressure is the top number on the reading. It measures the force of blood against your artery walls, while your ventricles, the lower two chambers of your heart, squeeze, pushing blood out to the rest of your body. Your diastolic pressure is the bottom number on your reading. It measures the force of blood against your artery walls as your heart relaxes, and the ventricles are allowed to refill with blood. Diastole, this period of time when your heart relaxes between beats, is also the time that your coronary artery is able to supply blood to your heart. During steady-state exercise, the arteries start vasodilating. This helps lower the blood pressure during exercise. However, this is opposed by the increased cardiac output, which in return raises the blood pressure as it is pumping out more blood faster. The systolic blood pressure results in rising during exercise, and the diastolic pressure stays the same or lowers a little. Thermoregulation is a process that allows your body to maintain its core internal temperature. When exercising, the body produces excess heat. The cardiovascular system is used to get rid of this excess heat. This is achieved through sweating and the enlargement of blood vessels near the surface of the skin. This allows heat loss as the sweat on the skin evaporates, cooling down the skin's surface. The blood vessels vasodilating near the surface allows heat loss to be gained through convection through the heat of the blood. Venous return is the rate of blood that returns to the heart. Veins provide a solution to the problem of low blood pressure in venous blood. Valves are spaced at intervals within the veins to stop a backflow of blood happening while en route to the heart. Because of low venous blood pressure, the veins compress, and in the case of steady-state exercise, muscular contractions help the veins with the venous return. Stirling's law. Stirling's law states that stroke volume increases in response to an increase in blood filling the heart, as stated by Adams et al. 2010. With an increase in blood filling the heart, this then leads to the stretching of the ventricular wall, which causes the cardiac muscle to contract with more force. This may also lead to an increase in stroke volume, as well as there being bigger contractions during exercise in the cardiac muscle. This all adds up to the reduction of heart rate in trained athletes, allowing for longer filling phases during diastole, so the stretch of the cardiac muscle is bigger, finally increasing the stroke volume. The tidal volume is the amount of air ventilated in or out of the lungs in one breath. It increases dramatically during steady-state exercise due to the body's demand for more oxygen and the need to offload increased levels of carbon dioxide. Tidal volume changes during steady-state exercise as the body needs more oxygen to keep the muscles working, so you start taking deeper breaths. This happens as the baroreceptors, chemoreceptors, and proprioceptors all detect change when exercised. Tidal volume changes during steady-state exercise as the body needs more oxygen to keep the muscles working, so you start taking deeper breaths. This happens as the baroreceptors, chemoreceptors, and proprioceptors all detect change when exercise starts. These then send signals to the dorsal respiratory group and the vasorespiratory group, which are in the respiratory control center in the medulla oblongata. This leads to an increase in rate of breathing and depth of breathing as the body is adjusting to the levels of exercise. The signal is then sent to the external intercostal muscles via the intercostal nerves, which increases the rate and depth of breathing. For the increase of tidal volume, it's the dorsal respiratory group that affects the depth in breathing, which increases the tidal volume at exercise. A lot of Mo Farah's training will be focused on increasing his tidal volume to allow him to get more oxygen in and out per breath when performing. This is because having a bigger tidal volume allows your body to get more oxygen around the working muscles quicker, stopping them fatiguing. Furthermore, testing has been done and shows that the average tidal volume of athletes is around 233 millilitres, whereas average people have a tidal volume of 113 millilitres a breath. The oxygen dissociation curve is a graph that shows a relationship between the percentage of oxygen saturation of blood and the partial pressure of oxygen. During steady-state exercise, increased temperature and lower blood pH concentration affects the oxygen-hemoglobin dissociation curve in such a way that more oxygen can be unloaded to supply the active muscles. This allows for participants to work longer periods of time. The main energy system used in steady-state exercise is the aerobic energy system. This works by breaking down adenosine triphosphate to create energy. ATP stands for adenosine triphosphate. This is important as our bodies use it to create energy. One way we use adenosine triphosphate to create energy is through an exothermic reaction. This is where a single piece of phosphate breaks off the adenosine triphosphate, leaving behind adenosine diphosphate. It is broken off as the enzyme ATPase is released, which causes the separation. The phosphofructokinase then detects a buildup of adenosine diphosphate. It then starts to break down glycogen into glucose. Then the glycogen phosphorylase finishes the breakdown of the glycogen into glucose. The glucose then turns into pyruvic acid, which gives off 2 moles of phosphate. This allows 2 sets of adenosine diphosphate to turn back into adenosine triphosphate. However, there is oxygen this time, which means the pyruvic acid and coenzyme A gives acetyl CoA by detecting O2 and pyruvic acid. This moves on to the stage 2, where the acetyl CoA binds with oxaloacetic acid to make citric acid. The citric acid then enters the Krebs cycle. The Krebs cycle gives off 4 things: oxaloacetic acid, 2 moles of phosphate, which are then used to make 2 sets of adenosine triphosphate, CO2, and hydrogen. The hydrogen is taken into stage 3, where it has 2 transport enzymes, being NAD and FAD. NAD and FAD then bind with the hydrogen to create NADH and FADH. The NADH and FADH then travel along the electron transport chain and are split into 2 separate things.